Okay, Rob here with another round of programming preparation for a big N interview. Last time we did this, we were implementing a binary search using integers. And in this time around, I think the next logical step would be to look at a sorting algorithm. So what's a sorting algorithm? It's what it sounds like. It's an algorithm that takes a vector of information and sorts it. In this case, we're going to stick to integers because integers are easy. And we're going to consider, before we going into the implementation, we're going to first talk about types of implementation because you want to look at efficiency here. So when you go about writing a sort algorithm, there's many ways you can go about doing it, and the most naive approaches are the easiest ones to implement, but they're also the most inefficient. So big O and squared, a quadratic implementation. That's going to be something that grows very fast, not efficient, and that's what most people kind of think of when they think of doing things for the first time ever in terms of sorting. You go through each index and you just swap it with its appropriate point in the array, and you keep doing that until you have this situation where you get to the end of the array or vector, and then you have to do a check from beginning to end, make sure every single one is in the right spot, and then you just keep on sorting it until you get there. Or you could do a bubble sort. I mean, there's different flavors. You can look them up, bubble sort, and things of that nature. So what we're going to implement is we're going to do Quicksort. Quicksort's the best one when you ask a CS200 student. I mean, there's Radix sort and a couple other accounting sorts as well. But let's stick with Quicksort. So what is Quicksort? Quicksort is implemented in a, if I recall correctly, big O n log n efficiency. And what it essentially does is it's a divide and conquer approach. And it looks at partitions of an array or a vector, and it begins separating values within a partition based off of a pivot value. Anything that is less than that pivot value is moved in front of that pivot value, and then anything that is greater than pivot value is moved to the right of it. And then you proceed to implement at the partition within left of the pivot value and then within right of the pivot value recursively. So it's very similar to binary search. Instead of searching for things, though, you're binary. You are going into partitions and actually making updates to that. So let's go ahead and get started, shall we? So this is, make sure we're in the right place here, Vim Harvey 2 for Big N Interview Prep 2. And let's go ahead and clear out the previous code. Not using any music because apparently using classical music isn't exactly keeping you safe from copyright, so I'm just going to not use any music. But if you want to listen along with me, I'm currently listening to some, what is this called? Infected Mushroom. Okay, so let's start again with understanding of what the signature is going to look like. We're going to pass it a vector. We're going to do amendments to it. So really, we just need to pass it the vector. So let's. It's going to be a void. We're not returning anything. We're just doing stuff to it. I'm going to call it Quicksort. Passing it a vector by reference, and we'll call it data again. Easy peasy, right? And then it's going to be the same thing like before with the binary search. We're going to have a helper, Q helper, and we're using it the same way we did in the previous video, where you are going to have to track where we are. So let's look at having another left index and a right index for the params. And again, like the last time, broken record over here, you're just going to call the function. You don't even need to use a return. Pass the data. 0 and our end is going to equal the size minus 1. So data size minus 1. And then let's do a test here. So let's give a vector t1 equals a new vector of integers. Let's push back some random variables now. So random variables in the sense that they are not sorted. Push back 11. Yank this Okay, let's update those numbers. 1, 10, 7. All right, so we expect. Let's do the iteration. So for the size, let's do a for each in C++11 because I didn't even remember how to do that. Okay, so for each integer val that is in T1, cout. I'm pretty sure that's actually not right. So far as the for each nomenclature, this is why we're here. Cout is going to equal val and L. Looks about right. And then Q helper, let's just do nothing. So update the makefile. All right, cool. So that is how you do it. Neat. My memory is not as rusty as I thought it was. I'm looking for vim rv2.cpp. Okay, so let's go about doing it. So again, what I was describing was a recursive call. So let's start at most people say base case. I want to dive right into the meat and potatoes. Okay. So like the binary search, we need to know where our pivot value is. Now, normally when you choose a pivot value, you want to use a random number generator to get your best performance because honestly, the numbers, like the nature of the sort for the data that you're already passing it will impact the efficiency. When I say big O n log n, that's the average case. It could be up to n squared if the numbers are such a fashion. But you can read CLRS on the details of that. But for the case of this implementation, I'm just going to go ahead and hard code the pivot value to be the mid value for demonstration purposes. And by mid value, I don't mean the middle value of all the values in that partition. I mean whatever values at the middle index of that partition. So when you do the pivot sort, you're going to have any number really of numbers to the left and to the right of the pivot. So let's do that. So let's call it not mid index. Let's call it pivot index. So int piv index. It's going to equal, again, rind minus lind divided by 2 plus the offset of lind. And then the actual value, pval, is going to equal data piv index. All right, nothing bad there. I'm going to do some shorthand pivin. All right, cool. So now what we need to do is iterate through partition to place values around p-value appropriately. Hopefully that makes sense to you. If it doesn't, then I'm a terrible teacher. Okay, so how long do we want to do this? So we're going to do a for loop where the beginning I is going to be equal to our left index. I is going to be less than or equal to rn because rn will be inclusive, and then I gets incremented. So we're going to need a swap function to make it easier readable, because that's what we're going to be doing. We'll be swapping things around. So the way, a good thing to do practice-wise and style-wise when implementing a quicksort is to place the pivot value at the beginning of the partition and just swap it with whatever value is there, and then do the comparison. So actually, we'll go to, well, yeah. So let's code up the swap. So void swap, and you're going to need the vector. You're going to need index 1 and index 2. So in A, int, and B. And just go ahead and get going. So int temp is going to equal int B, data, or really not that, but the data that's there. So data in B will equal data at int A, and then data at int A will equal the temp value because in B has already been rewritten with whatever values had in A, and that's that. The data has been swapped. So let's do the swap. So we swap p-val to beginning of partition. Okay, so let's do it. Swap, pass our vector, and then our index is going to be the L index because we want to put it at the beginning of the partition, and we're going to pivot it with piv index. Don't use p-val, use piv index, because the way we implement it is swap. We're swapping numbers at those indices. So now that that's swapped, let's go ahead and implement the if statement. Before we start writing code, let's think about what we're doing. So now that the pivot value is at the beginning, we can actually do this +1. And what we're going to do is check the value that we're looking at and what we're concerning ourselves with. And if it is less than pivot value, you're going to swap it and then move the pivot value back to where the last swap was made +1. So what you're doing is, and then if that's not the case, if the pivot value is in fact less than the value we're concerned with, you just do nothing and move on. And what that does is it allows us to iterate through the partition in a linear fashion and place values lower than the pivot value before the pivot value in that partition. And then the inaction of moving something when it's greater than, that maintains the integrity of anything to the right of the pivot value is in fact greater than the pivot value itself. So we need a way to track where we're putting it. That's what the pivot index is all about. So since we did that swap, piv index needs to be updated. It's going to be equal to ln +1. No, it's going to be equal to ln because our current pivot value is there. So if the data at the current iteration variable I at the current index I is less than, we don't care if it's equal to, but if it's less than our p-value, then we want to move it. So just look at the actual value. Okay, it's there. If it's there, we need to do two things. First, we need to put it where the current p-value is, or the p-index really. So swap data with I and piv index. Now we need to update the piv index, and then we swap the piv index back, the piv value back to where it should be. Oh no, it should be I. Because remember, we did a swap where we moved the pivot value to where the number we are currently concerned with the actual pivot value. So now I maintains the pivot value. You increment the pivot index and you move the pivot value to the new one. And then else, you don't do anything. You don't need to worry about updating pivot index because we're not doing any swaps. And then you just move on. So that should be the end of that. So once we've done this for loop, this partition is sorted based on p-val, right? Now we make a recursive call based off of where the p index ended up being at when you finish that traversal. So you need to do it for the lower half and the upper half. So you call it again. So you go q helper data, and then the first iteration. Let's look at the lower half. Okay. Let me comment this in there. Now work on lower half or lower partition. I shouldn't say half because literally it could be any number of values in the lower partition. So data, low bound, so lind maintains, just like our binary search. And then the right side is going to be amended to not the middle value, but to the pivot value -1, not unlike the binary search. So p-val or p-ind, piv-ind -1. And then now work on upper partition, q helper beep, 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 beep. Data piv end +1 r end. Now, just like with our binary search, we need to understand when we're at a point in our partition where we don't want to partition anymore. And that is, surprise, surprise, when our R end is to the left of the L end. So it should be the same thing. And then you just return, because it's a void function, so we're not actually returning any value. So that's a divide and conquer. As you see, the first time we go through it, we iterate through the entire partition, swapping out things on that first layer of pivot index. And then, based off of that swap, once that sort has been made at the first level, then you do a swap. You do that same thing on the left half and then the right half. Before you even touch the right partition, rather, the entire left partition is spliced down to the one element level and is sorted out. So by the time you get to calling the upper partition, the entire lower partition has been sorted. So now that's done. Let's call it. So let's call Quicksort T1. And now for int ampersand val in T1 cout val. Let's make. Let's see if we have any bugs. Okay, we have a bug. I forgot to add. I didn't spell my data parameter right. It has that underscore, so there's one there, and the other one is right there. Okay, let's try it again. Make, and I think that should do it. Execute at AX1, and now we're sorting it, and there's a sec fault. So let's see what's going on here. So we have a size 1, 2, 3, 4. So we're going to pass it through Quicksort, and Quicksort is going to pass it 0 and 3. So we go through data. Oh, here we are. A typo right there. I put an equal sign instead of a negative sign because of a fat finger, and I'm also operating without glasses. And there you go, sorted. 1, 7, 10, 11. Easy peasy, right? If you guys want to look at the code, I should probably start uploading these, but for now, just take a quick little look-see. Look at that. Not very different from your Quicksort or your binary search and your binary helper. Very similar. And if you want to read more about the details, look up CLRS's chapter on the Quicksort. There's also another implementation, and I want to say the Pragmatic Programmer. But that's all I got for you today. See you next time.